Hey guys, hope everyone's doing well. So we have a video here for if you were absent from school on Thursday or if you missed school on Friday. I'm going to cover everything we did in those 2 days in this video. And in those 2 days we really focused on different types of transformations. So we'll talk about reflections, we'll talk about translations, and rotations. And if you weren't here Thursday, I would stay for the video now and then skip the second half of the video. If you weren't here Friday, which is a lot of you, then I would maybe skip through the first part if you're comfortable with it and go into the second part of the video to get those notes. The nice thing about transformations is we've talked about them throughout the year, so we have a good base for them, we have a good foundation, but we're going to go into a little more detail for some of them. So we're going to start with a reflection. Now as we're going through this video, I have a slide presentation that I've shared with you that you can follow along, and you can pause the video if you need to take notes, do whatever you need. So a reflection, we're going to start with slide 1. A reflection we've defined in the past as a flip over a line. We call that the line of reflection. And what happens is the line of reflection is going to, when you reflect over it, you're going to be in a new position but the same distance away from that line of reflection. So there's really two scenarios, and we call this a reflection in a line. So the first scenario, say we have line L. If you're on the line of reflection, point A, and you reflect, you're going to stay where you are. So that scenario, if you're on the line of reflection, the pre-image and the image are the same. Easy as that. Second scenario, say we have line M. If you're not on the line of reflection, like point B is not on the line of reflection, but if we reflect over the line of reflection, so B prime will be somewhere down here, this line of reflection ends up being the segment bisector of the segment from B to B prime. It's actually the perpendicular bisector as well. So it's going to not only make these congruent, but these will be right angles. And that's because when you reflect over a line, you're the same distance away from that line. And to find the distance from a point to a line, you take the line, or you take the segment that's perpendicular from the point to the line, so the perpendicular, but that distance will be the same, hence making this line of reflection the perpendicular bisector of segment B prime. So that's something we can use when we're not reflecting over familiar lines. So keep that in mind. Those are two scenarios here. So go on to slide 2. Slide 2 is all just basic reflection rules that have a nice pattern to them. We've talked about reflecting over the x-axis. We've talked about reflecting over the y-axis. We've talked about reflecting over y equals x. We never talked about reflecting over y equals negative x, but the rule, if you have point P, which is x comma y, then when you reflect, it's going to become P prime, just like when you reflect over y equals positive x, you switch your coordinates, but now they're going to become the opposite side. And that's a nice rule to know if you're reflecting over that line. And you could do examples of those. We've done plenty of examples of those in the past. What we're really going to focus on for this is what happens if it's not one of those nice rules. So on to slide. Actually, no, before we do that, sorry. Let's do a little practice with these. Slide 3. Yes, slide 3, we have y equals 2x minus 6. I don't think we've done a lot of reflecting actual lines. We've done like points and polygons. So this is why I want to practice a little bit with these. So let's say we have the line y equals 2x minus 6, and we're reflecting over the x-axis. We can still use those rules. The rule for the x-axis, your x and y stay where they are, but y becomes the opposite. So y equals 2x minus 6. X and y stay where they are, but y becomes the opposite. So our line of reflection is the x-axis. Now we have the opposite of y after we reflect. So our reflected line, when we solve for y, multiply everything by -1. This would be your reflected line. And you can go ahead and graph your original line right here with your reflected, see how they relate. The x-axis will be your line of reflection. It also says on that slide we want to try to reflect over the y-axis. So we can do the same thing, take your original line, and the rule for the y-axis is y stays the same and x becomes the opposite. So negative x times 2, well that's just negative 2x, still minus 6. So this would be reflecting over the y-axis. That's your line of reflection here. And part C, we just want to reflect the line, or reflect over the line y equals x. So y equals 2x minus 6. We talked about this in class. This is the inverse function, if you remember inverse functions from Algebra 1. So reflecting over this line will give you the inverse function. It's a good thing to know. So when you reflect, the rule is that your x and y switch. So x equals 2y minus 6. You can bring the 6 over, divide everything by 2. I like y on the left. So you'll end up with y equals x over 2 plus 3. And that would be your reflected line over the line y equals x. Original, reflected, also original function, inverse function as well. So now we can move on to what happens if it's something that we don't have a special rule for. How can we find either coordinates or equations, things like that. So we're going to start with a polygon. So on to slide 4. We are given a quadrilateral. The quadrilateral has coordinates. J is 2, 3. K is 3, 2. L is 2, negative 1. And M is 0, comma 1. And I did not grab a graphing whiteboard with me, so I'm going to have to make my own coordinate planes. We'll have to deal with this. X and Y. So let's go ahead and graph our original quadrilateral. Let's count by, what are we going to need here? We'll count 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. Don't think we need that. So let's graph our coordinates. Our original quadrilateral, we have 2, 3. We have 3, 2. This was J, this was K. We have 2, negative 1. That's point L. And 0, 1. That is point M. And this is our quadrilateral. So J, K, L, M, if my marker wants to work. There we go. This is M. Now we are reflecting this over the line y equals negative 2. That's what we're told. So go down negative 2. Here's our line, y equals negative 2. We're going to reflect over that. So a reflection over this line. We don't have a special rule for this line, but we do know that this line will be the perpendicular bisector of the segment connecting the pre-image to the image. Meaning, point L, you're going to go down, and you're going to end up with L prime. Now you're going to need to be perpendicular to this line then, the segment connecting L to L prime. So perpendicular to a horizontal line is vertical. So L is just going to go down vertical, the segment connecting to the image. So going down, you're 1 unit away. So you're going to be 1 unit away going down here. This would be congruent to this. So L prime would have the units. We're going to be still the same x, 2. And then we're going to be down 1, 2, negative 3. Then if we look at, and maybe we'll do this in red, if our markers are going to work today. Here we go. So point K, again, you're going to be perpendicular to this, so you're going to be vertically going down. You're going to go down 1, 2, 3 units for K. That's the distance from K to the line of reflection. So that means K prime is going to be 1, 2, 3 units down below the line of reflection. So 1, 2, 3 units down. We'll do that in blue. That's K prime. Remember, these segments would be congruent because it's the perpendicular bisector. So K prime is going to be 1, 2, 3, comma, negative 1, 2, 3, 4, 5. 3, negative 5. And then, oh sorry, k was supposed to be up at 2. So k went down 1, 2, 3, 4 units. This should be negative 6. I think my graph shifted a little bit. This marker does not want to work. So this should actually be down at negative 6. This should have been up at 2. I'm a little bit off. Come on. Okay. So then point M, if we count, point M is 1, 2, 3 units away, vertically going down. So 3 units away. The M prime is going to be 1, 2, 3 units away. So point M would be right here, or M prime would be right here. And we would have 0 for M prime. 0, comma, negative 1, 2, 3, 4, 5. Negative 5 for M prime. And then to find J prime, you're going to count, going vertically down, so you're down 1, 2, 3, 4, 5 units. So you're going to be 5 further down than negative 2. We'll have the same X, 5 further down, so you're down 2, then 1, 2, 3, 4, 5 further. Right here, that's J prime. Make your new quadrilateral, and you're at 2, negative 7. So here's your final coordinates, and you can see the reflection. You're reflecting over the line, y equals negative 2 there. So the main thing here is looking for, and we showed it with these two. I think it would have become messy if I did the others. So, but you're the same distance away from the line of reflection, but you need to be perpendicular as well. So we can use that type of thinking for lines that might not be horizontal, because not every line is horizontal. So let's go on to our next slide, our next problem. We are reflecting now the segment with the points. A is negative 4, 3. B is, T is a T. Segment at is 1, 4. And we're reflecting this over the line y equals x plus 1. So here's my coordinate plane. And we are going to go, let's graph these points. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3. We're at negative 4, 3. That's A. We're at 1, 4. This is T. We are reflecting over the line y equals x plus 1. So here, here, here. Maybe a different marker. We are here, here, and here. So we are reflecting over this line. Y equals x plus 1. So to reflect over this line, let's start with point T. To reflect over, we're going to be T prime will end up being the same distance away from our line of reflection as T. So this is going to be congruent to this, and it's going to be the perpendicular bisector, so these are going to be perpendicular. So in order to find T prime, our first step is going to be to try and find the equation that this segment falls on. In order to do that, we need to find a slope that's perpendicular to this line, and we should see pretty quickly that slope is negative 1. So our equation of the line that's going to go through T and T prime, because that'll be the segment that's bisected by the line of reflection, it's going to be y equals negative x plus, well, we don't know b yet, but we can find b, because we know the line's going to go through the point 1, 4, meaning y is 4, x is negative, well, x is 1, so it becomes negative 1, so b is equal to 5. So the equation that's going to go through point T and is perpendicular to the line of reflection is negative x plus 5. Now if we make a system here with the line of reflection, then we can find the point that these two lines will intersect, which would be this point. And then we can find the distance from T to that point, and then get the distance from that point to T prime. We'll know where T prime is. So here's your system. Solve with elimination. 2y equals 6, y equals 3, If y is 3 here, x is 2. So that point is 2, 3. We'll call that point M. So to find t prime, I'm going to take, this is M, I'm going to take point T, and because my coordinate plane isn't the best, normally I would just say make a little right triangle here, because you can count the horizontal and your vertical change, and then you can make a congruent triangle right down here, and then it'll tell you exactly where this is. But really what you're doing is saying M is like the midpoint of segment T to T prime. So from T you change by going up 1 to M, so T prime is going to be 3. You go down 1, so you're going to end up with a 2 here for your T prime. So T prime would be at 3, 2, which is right about here. And then you're going to have the same distance. You could either make those two little congruent triangles. You can think of it as M as your midpoint between the segment T and T prime. Now we're going to do the same exact thing for A and find A prime. So for A, we know A's coordinates, and let's take away some of our work. So T prime was 3, 2, I believe. Now for A, we're going to have the same slope. Ooh, not plus B. Same slope, but we need to find A. So y is 3 equals 4 plus b. So b is equal to -1. Y equals -x minus 1. Make a system with our line of reflection. So we're going to have our system here. Elimination is great again. 2y equals 0. Y equals 0. If y is 0, then x is going to be -1. And there's your coordinates. 0, -1. Call this point P. So 0, -1, sorry. -1, 0. -1, 0. That's point P. From A to P is going to be the same distance from P to A prime. So that's the midpoint. A was -4 to 3. So you went up 3. So A prime, you go up 3, is going to be 2. You went down 3, so you're going to go down 3. So it's going to be 2, -1, 2, 3. We're right about here. And that would be the same. And that's your A prime. Again, you could make these little like right triangles, make them so that they're two congruent triangles, because then your hypotenuse will be congruent to one another. But A prime, I like the midpoint as well. A prime would be -4, 3. And you're all done. Alright, our last one on the slides is to reflect over a couple lines. So I'm going to let you try that one on your own. If you have questions about that, I can show you the work for it. But to save you a little bit of time, I'll give you your final answer, and then you can see if you get it right. If you don't get it right, we can always talk about it in the future. But this was where you had the point G was -1, -4, and then you're reflecting over y equals -x, and then you're reflecting after that over y equals 2x plus 3. So you can try that one on your own. Your final coordinates for this one, let's see. Oh, I don't have them written down, so I guess we're going to do this one together. So when you reflect G, -1, -4, over the line y equals -x, we know the special rule for that one. So our special rule is to switch, called G prime, switch them and make them negatives. So G prime is 4, 1. Then, that's after reflecting over this. Now reflecting over the line y equals 2x plus 3, your y and your x. We are at G is 2, 3, 4, 1. 1, 2, 3, 4, 1, 2, 3, 4. This is G prime. We're going to reflect this over the line 2x plus 3. So we're going to go here and up 1 over 2, down 1 to left 2. We're going to reflect over this line. So for G, to be perpendicular to our line of reflection here, our slope that's perpendicular is -1/2. So we're going to end up with y is equal to -1/2 plus b. We know G prime's coordinates. 1 is equal to -2 plus b, b equals 3. So y equals -1/2 plus 3, and we can make a system y equals 2x plus 3. Now you can solve this system. I think someone in class noticed two equations have the same y-intercept. That's the solution to the system. So there we go. 0, 3 is going to be the point that is the solution to those two equations. So this distance, 0, 3, we'll call that M here. So point M would be the midpoint of the segment connecting the image, pre-image to the image. So we take G, in this case it was G prime, because we had already reflected. So to go from G prime to M, you go down 4, so you would continue to go down, G double prime. So go down 4 again, -4. You go up 2, so you're going to go up 2 again, so you're at 5. So your final coordinates will be -4, and then 5, which would actually be right here. And those distances would be the same, could just be the same distance from the line of reflection. Okay, with that, we are going to be all done, and we're going to move into translations now. Alright, so translations. With translations, this is what we started on Friday. Translations, we've talked about in the past, and this is slide 7 on that slide presentation. We defined it as a function that maps each point of a pre-image to an image along a vector. So now we can use vectors. We talked about vectors. We call this a translation vector, and there are a couple of requirements. Each segment joining a point to the image, so the pre-image to the image, has the same length as the vector, and each segment is parallel to the vector. So if we have a segment AB, and we're translating this segment A prime, B prime, the distances are going to be the same to your translation vector, and they're going in the same direction. So everything moving in the same direction with the same magnitude, the same length, the same distance here. That's how a translation works. We use notation for translation. So if we have P, X, we would translate, we use vector notation. By vector AB, that means you're going to take your X, and you're going to add whatever your vector was, and you take your Y, you're going to add whatever your Y component is, and then you'll have your final point. So let's go ahead and we'll do the first one just to get a little example done. If we have a triangle FRE, with vertices, F is -1, -4, R is 6, 2, and E is 5, -5, we can translate. We're going to use the vector -3, 2. So all you're going to do, if you're on the coordinate plane, you can simply draw the vectors in. It might be easier. But if you're not on the coordinate plane, you're going to take F, -1, -4. You're translating by -3, 2, which is going to end up being F prime. Well, it's going to be -1 plus -3, which is -4. -4 plus 2, which is -2. So there's your F prime. Your R was given as 6, 2. And you're going to translate by the same vector. Everything's being translated by the same vector. So R prime is going to be 6 plus -3, which is 3. 2 plus 2, hopefully we get 4. And then E, we have 5, -5. And we're going to translate by -3, 2. It's a vector, not an ordered pair. So we have e prime, 5 plus -3 is 2. -5 plus 2, we should get, hopefully, -3. So these are your final coordinates. And on the coordinate plane, you can use that vector notation of -3, -3, 2, which would look something like that in standard position. Roughly about that. So everything's going to translate up and to the left. Now we also can use, so that was slide 8, on to slide 9, we also can use translations to kind of describe a total composition of points, a composition of transformations. So composition of transformations is doing more than one transformation. So slide 9 says point P, which has the coordinates -1, 4, is reflected over the line y equals 3, and then reflected over the line y equals x, and we want to know what translation vector best describes this composition of reflections. So I'm going to draw a little coordinate plane here. I'll do this one on the coordinate plane. So y equals 3, 1, 2, 3. We're going to take P as -1, 4. Here's point P. And y equals +3. And then we're going to go ahead, y equals x. So when you reflect over the line y equals 3, it's just going to bring you down 1 unit below. Here's your P prime. So P prime is going to be -1, 2. Then we're going to reflect that over the line y equals x. So P double prime, that's going to end up being where you just switch your x and your y. So 2, -1, 2, -1. There's P double prime. And now you're trying to see what translation vector best describes going from the image, or pre-image to the image. So going from P, what translation vector best describes that? And if you compare the 2 points, that'll get you the x and y component a lot easier. How do you change going from 2 to -1? Or going from -1 to 2, because you're increasing, you're going from P to P double prime. So -1 to 2, you've gone up by 3. Going from 4 to -1, you've gone down by 5. So your x component is 3, your y component is -5, and you're all done. That's your vector component, or your component form for your translation vector. And that's really all we have with translations. On to rotations. So rotations, we're going to use a little bit of trig with these, so you can grab your calculators if you have one at home. If not, you can find a graphing calculator on the internet that'll work for you. So on to slide 10. Slide 10, it talks about a rotation. We've defined rotations. Rotations are defined as a turn through an angle x about a fixed point. The fixed point is called the center of rotation. So point P, point M. So when you're rotating M prime, this would be like your angle M that you're rotating. That's the turn about point P. So one possibility would be if you fall in the center of rotation, you're going to end on the center of rotation. That's kind of an easy case. The other case that we'll spend more time with is if you're not on the center of rotation, like M is not, when you rotate about the center of rotation, your pre-image is going to be the same distance away from the center of rotation as your image. You're not getting further away, you're not getting closer, you're not in any sort of way dilating this. You are staying the same distance, and you're changing by angle x. So that angle is created by the segment from the pre-image to the center of rotation, and then from the center of rotation to the image. Those two segments, they obviously share a common point. That would be the vertex of the angle of rotation. Angle of rotation is x there. So here's your angle of rotation. And we can use this for some special types of rotations. So our next slide, slide 11, it talks about some special rotation rules. So some special rules, we have the 90 degrees clockwise, and that's going to be when your x and y become y, negative x. They change places and your x value became negative. Your original x value, x coordinate, becomes negative. And you can do the 90 degree clockwise rule twice and you'll derive the 180 degree rule. And then you have your 270 degrees clockwise rule. Now these you can memorize, but if you're not doing an increment of 90, then they're not going to be the most helpful. So if we go past that now, and we try to rotate, now we're on slide 12, we are told to rotate line 2x plus 4, and part A says rotate 90 degrees clockwise about the origin. So those rules were for rotating about the origin. So 90 degrees clockwise about the origin. The rule for this, rotating 90 degrees clockwise, your x becomes negative and is now your y coordinate. So we had the equation y equals 2x plus 4. And your x is going to change signs and become your y. Y is just going to become your x. Then you're going to solve for y. So subtract 4, divide everything by 2. So y is going to be negative x over 2 minus 1/2. You may notice in your original equation and your final, your rotated equation, their slopes are perpendicular to each other. Well, that should make sense because you're rotating 90 degrees, which is going to make a right angle between the two lines. They should be perpendicular to each other. So when you rotate this, you should end up with a perpendicular slope. Now the second part, we wanted to rotate 180 degrees. And rotating 180 degrees about the origin, our rule was, let's write our original equation down. They are going to stay in the same spot, our coordinates, so your y stays where it is, and x stays where it is, but they both change signs. So now we have negative and a negative. But if you multiply everything by -1, you're going to end up positive 2x minus 4. And that will be your new equation. Notice your two lines have the same slope, because rotating 180 degrees, you're rotating 90 twice. So you're going to end up with the same slope. You're perpendicular to the line that's perpendicular to the original. You're parallel to the original then. You have a different y-intercept though. You're not the same line. You are just parallel to it. Okay, that's how you can rotate a line about the origin, just using the same rules, but applying them into the equation. We'll do two more together to see how you can do increments that are not 90 degrees. And we're going to go about the origin though. So slide 13, it says